Okay, everyone, assalamu alaikum. Let's begin then. So, in the last session, we covered translation, reflection, and rotation. Today, we will do enlargement and also a number of practice questions, a number of past paper questions on transformations after that. So, we started with this. Translation is described by a column vector. We learned how to do transformations and how to determine how to identify whether there is a translation. We did some examples of that, and then we talked about reflection. Reflection is described by the line of reflection. We learned how to do different types of reflections. Reflection in x-axis or in any other horizontal line, reflection in y-axis or any other vertical line, reflection in y equals x, or reflection in any other line that has a gradient of 1, and also reflection in y equals minus x, and reflections in other lines that have gradient of -1, right? We talked about this. Then we also discussed how to identify a reflection. We talked about whether what's the difference, how would you identify whether it's a reflection or a rotation. Translation is easy to figure out because that just is very clear that the graph is shifted from one point to another. But differentiating between reflection and rotation sometimes is a bit tricky. And for that, what you generally do is you say, let's join the corresponding points on the image and the original object. If you end up getting parallel lines from that, then that means that's a reflection. Okay. And then how do you figure out the line of reflection? You find the midpoints of each of those lines, joining the corresponding points, and then you join those like this. This was the example that we did. We had two triangles given where one was a transformation of the other. How did we identify that it's a reflection? When we joined corresponding points, we got parallel lines that made it clear that it was a reflection. And then the midpoints of these lines, when we joined them, we got the line of reflection from that. Okay, so that's what we did. We talked about rotation next. Rotation is described by the angle, and then you also have to specify if it's clockwise or anti-clockwise. That's important. And the center of rotation. You need two things for rotation. We talked about this. We discussed a number of different types of rotations: 90 degrees clockwise, 90 degrees anti-clockwise. It could be about origin, it could be about any other point. And we learned how we could do it using this method that we had, that we have these four directions. If it's 90 degrees clockwise, up goes right, right goes down, down goes left, and left goes up, right? When you do 90 degrees clockwise rotation, in anti-clockwise, it's just the opposite of this, right? We learned how to do these rotations on this diagram. Also 180 degrees rotation, that's easier because you just invert the diagram about the center of rotation. So whatever is the distance of z on this side, it becomes the same distance on the other side like this. Whatever is the distance of y from the center of rotation, it becomes the same distance on the other side. And similarly for x, that's what we did. And how do you identify rotation? Again, you first of all figure out that it's not an enlargement or a translation. That's both of them are very clear from the diagram. We will discuss that as well today when we have covered enlargement. But how do you differentiate between reflection and rotation? When you join corresponding points, you get non-parallel lines, and that means it's a rotation. And then we also discussed how to find the center of rotation. We did that in this example. One method was using trial and error, that you just try some points, and mostly what happens is you can just identify that point right away as it is without having to draw anything, right? So we guessed this point. How the idea was, center of rotation is a point that has equal distances from the corresponding point. So for example, if you have this point as the center, the point C, its distance from R and its distance from R prime, it is supposed to be the same. Its distance from Q and Q prime, that's also supposed to be the same, right? So corresponding points, they have same distances from the center of rotation. So they basically mark a point like that. That's what we discussed. And then the other possibility was, if you find that difficult, or you cannot spot the center of rotation using that method, then the general method of doing that is that you draw perpendicular bisectors of corresponding points. The point where these perpendicular bisectors meet, that is going to be the center of rotation. So if you can't figure it out directly, then that's the general way that always works. Draw perpendicular bisectors of corresponding points, and then wherever they intersect, that's going to be the center of rotation. And then using that, you can find the angle of rotation as well. We discussed that. So this is what we've done until now. How to do these transformations: translation, reflection, and rotation, and how to identify these transformations. If you are given those transformations in the form of a diagram, how do you identify what transformation that is, right? So we've also discussed that. Now today we want to start with enlargement first of all, and then do some practice, some past paper questions after that. Now, what is enlargement? This is the only one of these four transformations in which the size of the figure changes. Okay. In the other three transformations, the size does not change. That remains the same. Okay. And enlargement is described by two things: center of enlargement and scale factor. Okay. Rotation had center of enlargement, and then the angle anti-clockwise or clockwise. Enlargement has center of enlargement and scale factor. These are two things that you need to describe an enlargement. Okay. Center of enlargement and scale factor. Now, how exactly does it work? Let's do some examples to understand this. So we have this triangle, and what we want to do is we want to enlarge this triangle with scale factor 2 and the center of enlargement at the origin. Okay. So with respect to the origin, we want to enlarge this triangle. Akif, we discussed that yesterday, how to find center of rotation. I quickly went over that today, as in I just showed you how we did this in the last class, but when we do some practice questions today from past papers, that will become clear, okay? When we do some practice questions from past papers today, we will do some examples there as well. But let's complete enlargement then, and then we go on to past paper questions after this. Okay, so it says enlarge A with scale factor 2 and center origin. So the center of enlargement is at the origin. This is the center of enlargement. Now the idea is we want to enlarge this figure with scale factor 2. Now how do you do that? Let's mark corresponding points as we normally do for any transformation question. Let's mark the corresponding points. We've got one point X here. We've got another point Y here, another point Z here. We've got these 3 points on this triangle, okay? Now you enlarge one point at a time. You look at the distance from the origin of this point X. That's 1 unit diagonally, right? So since the scale factor is 2, you make it twice the current distance. So it goes here and it becomes X prime. Okay. Another way that sometimes students find helpful is an enlargement. That from the center of enlargement, to think of it like this: how many units do you have to go right and up to get to the point X? 1 unit right and 1 unit up. So when you have a scale factor of 2, you multiply this by 2, and this will go to 2, 2. Okay. So this gets multiplied by 2. So now you have to go 2 units right and 2 units up, and that gives you the point X prime. Okay. But mostly it's fairly straightforward to do it from the diagram directly as well. You can do that. Otherwise, you can use this vector method as well. Similarly, for Y, for instance, from the center of enlargement, we have to go 2 units right and 1 unit up. Okay. So we'll have to go 4 units right and 2 units up. If the scale factor is 2, right? Whatever is the distance of Y here, just make that twice that, and you get to this point. This is going to be Y prime. Now, again, this is one way to do it directly from the diagram directly using the diagram. If you wanted to write it down, you would say y is 2 right and 1 up. Okay, so you could say y is 2 right and 1 up. So you could just multiply that by 2, that's the scale factor, and that gives you 4, 2. So y prime is going to be 4 right and then 2 units up, and that's y prime. And then finally, what about z? Whatever is this distance from the center of rotation, you just multiply that by 2 and you get to this point here. This is z prime. Again, if you wanted to think of it using the vector form, you would say z is 1 right and 3 up. Multiply that by 2, and that gives you 2 right and 6 up. So 2 right, 6 up, that gets you to the point z prime. Okay, and now you can draw this triangle x prime, y prime, z prime. This is the enlarged triangle. This is the enlarged triangle. Now, there are some properties that you have in enlargement that are important to understand. Look at each side. Look at each side of this these triangles, the corresponding sides. This was 1 unit. The horizontal side was 1 unit earlier. After transformation, it becomes 2 units. So it gets multiplied by 2. Vertical side was 2 units. After transformation, it becomes 4 units. It also gets multiplied by 2. So every side of the diagram is going to get multiplied by the scale factor. Its length is going to get multiplied by the scale factor. These are similar figures. This small triangle and this big triangle, these are similar triangles. So the properties of similar triangles, they're similar figures, they're also going to apply here. What were the properties? The ratios of their areas, that is going to be the same as the square of the ratios of their lengths, since these triangles are similar. Okay, keep that in mind. I will summarize this later on as well. But remember, whenever we have an enlargement, the two diagrams that you have, they're always similar figures. Okay. All right. So that was one example. Let's have a look at another. We want to enlarge this triangle with scale factor 3 now, but now the center is not the origin. Center of enlargement is something else now. The center of enlargement is -1, 3 in this case. Okay, -1 and 3. This is the point which we're saying is now the center of enlargement. Okay. Now, scale factor is 3. That means whatever is the distance of each point from the center of enlargement, it will get multiplied by 3. So for example, the point Z, it is 2 units to the right. It gets multiplied by 3, so it becomes 4 and then 6 units to the right. The point Z prime is going to be right here. Okay, that's the transformed point Z prime. Similarly, X is 2 units diagonally like this, or you could think of it using the vector form as well. It's 2 units right and then 2 units down, right? And then the scale factor is 3, so you multiply this by 3, and that gives you 6 right and -6 down. So that is where the point X is going to be 6 units right and then 6 units down. And that will take you to this point, 3 and -3. This is X prime, right? So you just multiply that by 3, you get to this point basically. All right. So that's X prime. Similarly, Y prime, how do you think about that? This is the distance of Y right now. Okay. We're going 3 units right and then 2 units down. Okay. So when you multiply this by 3, it's going to become 9 right and 6 down. You can do it mentally as well like that, or if you want to write it down, you can do that. You can say Y was initially 3 units right and 2 units down from the center of rotation, center of enlargement. It was 3 right and 2 down. You multiply that by 3. What do you get from that? You get 9 and -6. So now, in order to get to that point, Y prime, you have to go 9 units right and 6 units down. Let's see what that point is going to be. This is 7. Let's mark 8 here as well. 9 units right, that will be at the point 8. And then 6 down, that will take us to some point here. This is y prime. And now you can draw that triangle. The enlarged triangle looks something like this. This is your enlarged triangle, scale factor 3, with this point being the center of enlargement. This is what it looks like. Okay. This is your enlarged triangle. Make sense? Any problems with this? Any problems with this? Let's move on. Enlarge A with scale factor -2 and center 0, 3. Okay, so we enlarge A with scale factor -2 and center 0, 3. What's the center is now 0 and 3. That's this point here. Okay. The scale factor is now negative. What happens when the scale factor is negative? Let's think about this now. When the scale factor is negative, let's mark the points again. So we've got this point X, Y, and Z. Point Z is 1 unit to the right. Okay. When the scale factor is -2, what happens is the diagram is going to go on the other side of the center of enlargement now. Now it's 1 unit to the right. This point is going to go 2 units on the other side, and that is where the point Z prime is going to be. Again, you can think of it using vectors as well. Where is point Z with respect to the center of rotation? This is the center of rotation, right? 0, 3. Point Z is 1 unit right and 0 units up, down. You multiply it by the scale factor, which is -2. What does that give you? That gives you -2, 0. So from the center of rotation, you have to go 2 units left, and that gives you that point Z prime. Similarly, where is X? X is 1 right and then 2 down. 1 right and 2 down, right? 1 - 2 multiplied by the scale factor. Where is this going to go with respect to the center of rotation? -2 and +4. That means 2 units left and then 4 units up. And that is going to be this point here, right? This is X prime. And then finally, we've got Y. Where is Y? Y is 2 units right and then 2 units down. It's going to go like this here and here. This is going to be Y prime. You can do it using vector as well. You can say Y is 2 right, 2 down. 2 - 2 multiplied by the scale factor -2. What does that give us? -4 +4. So that means 4 units left and then 4 units up from the center of rotation. And that gives you that point Y. So this is Y prime. And now we can draw the enlarged triangle. The enlarged triangle looks something like this. This is the enlarged triangle with scale factor -2. It goes to the other side of the center of rotation. All right. And now you see when the scale factor is negative, number one, the figure goes to the other side of the center of enlargement, and also it becomes inverted, right? So the base was here earlier. Now that same length has gone there. So the figure is inverted, right? That's what happens when the scale factor is negative as well. The figure gets inverted, okay? And then let's have a look at this example. Now we want to enlarge this triangle with scale factor 1/2 and center -3,5. Center -3,5, scale factor 1/2. What's the center now? -3,5. Where's that point going to be? That point is right here. This is -3,5. That's the center of rotation. Scale factor is 1/2. Now, again, let's mark the points here. This is X, this is Y, and let's say this is Z. Let's start with Z. This is the distance of Z from the center of rotation. Where is this point going to go? It becomes half the distance, right? The scale factor is 0.5, 1/2. So whatever was the distance earlier, now it becomes half of that. So that point Z is actually going to come here. Okay, if you want to do it using vectors, again, you can say the point Z, it is 4 units, 1, 2, 3, 4, 4 units right, and then 2 units down with respect to the center of rotation. So it's 4 and minus 2. You multiply this with 1 over 2. What do you get? 1 over 2 times 4, that is 2. 1 over 2 times minus 2, that is minus 1. So you go 2 right and 1 down, and that gives you this point Z prime. Okay. Then next, X. X is 1, 2, 3, 4. 4 units right. 1, 2, 3, 4. 4 units down. Okay. So let's do it using vectors as well. 4 right, 4 down. Multiplied with 1 over 2, what do you get? You get 2 and minus 2. So now the point X from the center of rotation is going to be 2 right and then 2 down. So that comes here. This is point X prime. And then finally, you've got Y. Y is 1, 2, 3, 4, 5 right, and then 1, 2, 3, 4, 4 down. That's Y. 5 and minus 4. You multiplied with 1 over 2. 5 over 2 is 2.5, and minus 4 over 2 is 2, minus 2. So that gives you 2.5 to the right and 2 down. And that is going to be this point here. This is Y prime. So the enlarged triangle, it's still called an enlargement, right? That looks like this. But you see, the figure is actually smaller than before. So it's not actually getting enlarged, it's actually getting smaller. Why is it becoming smaller? Because the scale factor that we had was less than 1. When the scale factor is less than 1, when you multiply something by a number that's less than 1, the number gets smaller, right? The number gets smaller than that. So the diagram in this case as well, for that reason, it becomes smaller. Rather than becoming bigger, it becomes smaller like this. Okay? So that's what you get from this. Now that's how you apply enlargement. Now this is what we discussed there. So keep that in mind. When the value of the scale factor is positive, so we often represent the scale factor by letter K. Okay. If the scale factor is positive, the object and image are on the same side of the center. However, if the scale factor is negative, the image goes on the other side of the center of rotation. So if the original object is on one side, the enlarged object is going to be on the other side of the center of enlargement. And also the figure is going to be inverted, like we saw in that example. And then if the value of K, if the scale factor is between -1 and 1, if the scale factor is between -1 and 1, what happens in this case is you will see that the object will become smaller. So if the scale factor is, for example, 0.75, or if it's minus 0.5, for numbers that are smaller than 1 in terms of their magnitude, the object is going to become smaller. And if the scale factor is greater than 1 or less than -1, so -2, -3, for example, in these cases, the object becomes bigger. Okay, so these are important things that you need to take note of for enlargement. Okay, now that's how we apply enlargement. Okay, we've talked about that. Now, what if we had to do the other way around? That if we had a diagram given in which we had the original figure and the transformed figure, and we had to figure out what transformation that is. Now, enlargement is going to be very easy to identify because this is the only transformation in which the size of the figure changes, right? So if the size is changing, that means it is enlargement. So if A is being mapped onto B, you can clearly see that the size of the figure is changing. So this has to be enlargement. Okay, it has to be enlargement. Now, how do we figure out what enlargement exactly? So as we discussed earlier, in order to describe an enlargement, we need two things. Yes, we can say it's an enlargement, but then we need to write down what the center of enlargement is and also what the scale factor is. Okay, center of enlargement and scale factor. Now, how do you find center of enlargement? This is the idea that we have for that. We just join corresponding points. In order to find center of enlargement, all you have to do is join corresponding points. Okay. So that means join y with y prime, join z with z prime. Two are going to be enough, but just to confirm, you can join the third one as well. X and x prime. You see all of them, they are intersecting at the same point. This point where they are all intersecting, this is the center of enlargement. That's how you find the center of enlargement. Just join the corresponding points. The point where these lines intersect, that's the center of enlargement. Okay, so now we can say it's an enlargement with this point. It has coordinates 3 and 3. 3, 3 as the center of enlargement. Okay, so you write that it's an enlargement, then you write that 3, 3 is the center of enlargement. That's the second thing that you need to write down. And then what about the scale factor? How do you find the scale factor? What you can do for this is you can just see the ratio of corresponding points. Okay, see the ratio of corresponding sides. For instance, the smallest side, you can see this is xy. In the other figure, the smallest side is 2 units. In the original figure, it was 1 unit. So it's becoming twice the size. So take any side, any corresponding side. Okay. In the original figure, the smallest side was 1 unit. In the enlarged figure, the smallest side is 2 units. So it is getting multiplied by 2. Okay. So we can say with scale factor, either plus or minus 2. Okay. Either plus or minus 2. However, you can see the diagram is going on the other side of the center of enlargement. When does that happen? When the center of when the scale factor is negative and the figure is also inverted, right? Figure is inverted. The diagram is on the image is on the other side of the center. That means it has to be negative. So scale factor is -2 for that reason. Okay, that's how you identify an enlargement. This is the process for that. It's the summary of that. Now, how do you find the center of enlargement? You join corresponding points of the object and its image. The point where they intersect, that is going to be the center of enlargement. Okay. And then how do you find the scale factor? It's just the ratio of corresponding lengths of the image of and the object. So identify any corresponding sides, see what their ratio is, and that is going to be the scale factor. Okay, so if the scale factor is k, it's length of one side of the image with divided by the corresponding side of the original figure. Now, sometimes they will give you areas in the exam. Okay, they will sometimes give you areas in similar figure, areas in enlarged figures. What we do for that is we say k squared. That is going to be area of image divided by area of object. It comes from similar figures, right? Because the ratio of areas in similar figures, that's square of the ratio of their lengths. So if k is equal to this, for instance, k square is square of this, and we know that this thing and this thing, they are equal, right? So that is why k square equals the ratio of their areas. So these are two ways of finding the scale factor depending on what information you have. Mostly we use the lengths. Sometimes when they have areas given in the question and they want you to find scale factor, then you use this idea that k square is supposed to be area of the image divided by area of the original object. Okay. Image is the transformed figure. Okay. So that's how enlargement works. Now, we will have a look at some examples now, some past paper questions now. Before we do them, however, just some final points, some summary of these 4 transformations, the most important of which is how do you identify a given transformation. Now, this chart is extremely important because this is the tricky part in transformation sometimes. When you have to do the reverse working, that they give you a diagram and its transformation, and they ask you to identify what transformation it is. Okay, so how do you identify a given transformation? This is how your thought process is supposed to be. The first thing you notice is, or the first question you ask yourself is, do both the figures have the same size? The original figure and the transformed figure, are they same in size? If the size is changing, then the only possibility is that it is enlargement, right? If the size is changing, then in your syllabus, it can only be enlargement. It cannot be anything else. Okay. And if it is enlargement, then you describe it using center of enlargement and scale factor, and you do make basically write that description. You say it's an enlargement with a specific center of enlargement and some scale factor, which we have learned how to do. Okay. If the size is the same, however, if the size is the same, then the other three transformations are possible. Okay. Translation, reflection, and rotation. If the orientation remains the same, orientation means if it's a figure like this and it is just moved somewhere else, and you still have the same points in that same order, A being the leftmost point, B being the bottom right point, and C being the top point. If that is not changing there, the orientation of the object is the same, that means it's a translation. So it looks like a shift from one point to another, that you've just picked up that triangle and put that in another place. Okay, that's a shift. This is a translation. If that is not the case, if the orientation is not the same, what happens in that case? It could either be a reflection or a rotation. It could be one of these two. How do you differentiate between those two? You join corresponding points with straight lines. So if it's not an enlargement, not a translation, enlargement and translation, you can just spot them by just looking at the diagrams. Okay. Enlargement will have its size changing, and in translation, it would be clear that the figure is just being shifted from one point to another, keeping everything else the same. If both of those transformations are not what are happening, then you join corresponding points with straight lines. If you get parallel lines, that's a reflection, and you describe reflection using the line of reflection. If those lines are not parallel, then it's a rotation, and you describe rotation like this. You write down the angle and write down whether it's clockwise or anti-clockwise, and also write down the center of rotation. All right. This is how you would identify transformations. Okay, now once that is done, another thing that you will notice sometimes in questions would be that you would have combinations of transformations. You would have combined transformations. Okay, multiple transformations happening at the same time. Now, this notation is important. Let's say we have a transformation Rx, and this is the notation that we have for reflection in x-axis. We have another transformation which we're calling RD, and this is a reflection in the line y equals x. We have these two transformations. Rx is reflection in x-axis. Rd is reflection in y equals x. Okay. Now, if you have a transformation be defined like this, so if you have a transformation, if you have this transformation defined like this, RD Rx of A. Now, what that means is A is the original figure. It's the original object. A is the original object. You apply these two transformations on that object, and you get this transformed object. This is the image of that. This is the transformed figure. You are applying these two transformations, RdRx of A. Now, how do these transformations work? The order is important here. The transformation that's closest to A, that will apply first. So first of all, you will be doing reflection in x-axis here. Okay, so the first thing you would do in here would be reflect A in x-axis. Once you have done that, then you apply the second transformation. The result that you have from the first transformation, you reflect that in the line y equals x. So this notation, when you have multiple transformations written like this, the one that is closest to the object, that applies first, and then the one that's further away from that, like this. That's the order in which these transformations are going to be applied. So in this case, you would say first reflect A in x-axis, that's Rx, and then reflect the results that you get from the first transformation in the line y equals x, that's Rd. That's the order in these transformations are going to work. So where is the triangle B going to be if you're applying this transformation on A? What would happen would be you would first reflect this triangle in x-axis, and that would give you a figure that looks like this. So first you transform this in x-axis, you get this result. And then this result, you reflect in y equals x line. What is that going to be? Y equals x line looks like this. Right, this is the y equals x line. You reflect in this line now. 1 unit diagonally, and that goes here. You've got 1 point here. And then this point, 1, 2, and then it goes 2 units on the other side. This is another point. And then 1 and 1.5, 1.5. This is the other point. This is going to be your triangle B after applying those two transformations. Okay. So first of all, you reflect in x-axis, you get this, and then you reflect this in y equals x, and you get that figure. This is the final triangle B that we were looking for. Okay, so this order is important. The transformation that's written closest to the object, that is applied first. All right, let's move on. The last thing before we start past paper questions, sometimes you will also see inverse transformations. Inverse transformations. Now, what are inverse transformations? An inverse transformation is what will map the image back to the original object. Okay. For instance, let's take an example that we have done before. This rotation, for instance, we rotated this figure A 90 degrees clockwise about the origin. Okay. We rotated this 90 degrees clockwise. And we got the triangle, the other triangle. If we had to go back from this red triangle to the black triangle, what transformation would we have to do for that? We would just reverse it. The opposite of this would be 90 degrees anti-clockwise rotation. 90 degrees anti-clockwise rotation with the same center of rotation. That will be the inverse transformation that will map the image back to the original object. Okay, that's inverse transformation. So inverse transformation is one that gives you the original object back. So if it's a 90 degrees clockwise rotation, the inverse of that would be 90 degrees anti-clockwise rotation. And if it's a reflection, for example, if you're reflecting something in x-axis, in that case, if you reflect the figure back in the same line, you get the same image back. So for a reflection, the inverse transformation is that same reflection because that will give you that same object back. Okay. Now, that's the idea of inverse transformations. Now, let's see what happens in a number of transformations, what their inverse transformations look like. So that's the idea of inverse transformation, first of all, that it maps the image back to the original object. Okay, it maps the image and maps the image back to the original object. Now let's see what the inverse of these transformations would be. So if you're doing a translation AB, if you're doing a translation AB, let's try some numbers that might help you understand it better. Let's say you're doing a transformation 3, 5. So you're moving an object 3 units right and 5 units up. Okay, 3 right and 5 units up. How do you go back to the original figure? You do the opposite of that, -3 and -5, right? You go 3 left and 5 down. That will get you back to the original figure. So if you have a translation AB, the inverse transformation for that would be a translation -A minus B. That will take you back from the transformed figure to the original figure. Okay. If we have any reflection, the inverse would be that same reflection, right? Because if you reflect something in x-axis and you get some image from that, how do you go back to the same image? You reflect in the x-axis again, and you get the same thing back. Okay. So for reflection, inverse is also the same. If it's a 180 degrees rotation, inverse of that is also just 180 degrees rotation. Because if you have something, if this is the center of rotation, and let's say you have this point A and it's rotated 180 degrees, it will go to the other side, and this will be the image. If you want to go back to that point now, you rotate it 180 degrees again, and that will get you to the same point again. So 180 degrees rotation, its inverse is also 180 degrees rotation. Okay. If it's a 90 degrees clockwise rotation, 90 degrees clockwise rotation, its inverse would be 90 degrees anti-clockwise rotation. And if it's a 90 degrees anti-clockwise rotation, its inverse would be 90 degrees clockwise rotation. Okay, so if you're going clockwise, inverse would be anti-clockwise. If you're doing anti-clockwise, the inverse of that would be clockwise. And then finally, if we have an enlargement with scale factor k, for instance, let's take an example of that. Let's say you are doing an enlargement with scale factor 2, okay, with some center of enlargement. What would be the inverse of that? What would be the inverse of that? If you want to go back to the original figure, scale factor 2 multiplied every side by 2, right? If you want to go back to the original figure, that means you would have to divide each length by 2 now. Or in other words, multiply by 1/2 in a reciprocal of that. If you were multiplying by 2 earlier, now you're dividing by 2. So that's multiplication with 1/2. If the scale factor originally was 4, then the inverse of that would be 1/4, right? If the scale factor originally was 1/3, then the inverse of that would be 3. So you just take reciprocal of that, and that will give you the inverse transformations scale factor, inverse enlargement scale factor. So in general, if you have an enlargement with scale factor k, its inverse would be an enlargement with scale factor 1/k. That would be the inverse of that. Okay, just take reciprocal of that, and that gives you the result. Okay, that is the inverse enlargement, inverse transformation. Is that all right? Any quick questions on this before we start with the past paper questions? Any problem with this? No? Okay, let's try some questions now from past papers. Remember, you will see questions in past papers on stretch and shear sometimes. They are not part of your syllabus. You'll also find questions involving matrices in transformations, they're also not part of your syllabus. Okay, so matrices you can skip, and also any question on stretch or shear, those uh, words, wherever you see them, you can skip those parts. They're not part of your syllabus. Let me write them down here. So matrices, they're not part of your syllabus. Stretch is not part of your syllabus. Shear is not part of your syllabus. Okay, so you will find questions in past papers involving these things. They can be skipped. You don't have to do them. Okay, now let's have a look at this transformation. This question. The diagram shows triangles A and B. We have this triangle A and this triangle B. We want to describe fully the single transformation that maps A onto B. Now, how do you do that? How do you figure out what transformation it is? Now, number one, think of whether it's a translation. It's not. The orientation is changing, right? The longest side was like this earlier, now it's vertical, so it's not translation. Is it enlargement? No, because the size is not changing. The size is the same, so it's not enlargement as well. So it's either reflection or rotation, right? We're not sure which one of them it is, but it's one of those two, either reflection or rotation. How do we identify which one of the two it is? You join corresponding points. Okay, now how do you figure out corresponding points? The point opposite to the longest side, they have to be corresponding, right? So I can say, let's say this is x in the original figure, and this is x prime. These are corresponding points. And then the point that is closer to x, so we have 2 points now, 2 other points. One is close to x, the other is not that close, not as close to x. So if we call this y, that means this is the corresponding point y prime. And then if this is z, then this is z prime. All right, these are the corresponding points. Now let's join these corresponding points and see whether we get parallel lines or not. Okay, if we get parallel lines, that's a reflection. If we don't get parallel lines, then that's a rotation. Okay, if we join z and z prime, we get this line, x and x prime. That's this line. Okay, y and y prime. That is this line. Okay, so these are all parallel lines. Since these are all parallel lines, that means it is a reflection. Okay. Now, if you don't do this just by looking at it, it might seem like it is a rotation, but it's not a rotation, it's a reflection. Okay. You could also identify this using the order of points. Remember, we also talked about this. In the original figure, we are saying it's x, y, z in the clockwise direction. So if you go clockwise, you get x, y, z. In the transformed figure, x, y, z is if you go in the anti-clockwise direction. So the direction of these vertices is changing. It's reversed. That only happens in reflection. It does not happen in rotation. Okay, in rotation, the direction of these points remains the same, right? In this case, it was clockwise earlier. Now it's becoming anti-clockwise. All right, so it has to be a reflection. How do you figure out the line of reflection now? How do you figure out the line of reflection? Find the midpoints of these lines. This is the midpoint of y and y prime. This is the midpoint of x and x prime. This is the midpoint of z and z prime. No. This is the midpoint of z and z prime. Join these points and see what line that you get from that. This is the line that we get in which these triangles are reflected. Okay, so what do we say then? How do we describe this transformation? Just give me a second. Okay, so how do we describe this transformation then? We say it's a reflection. And then you have to write down the line of reflection. It's reflection in the line y equals, it's a common line that you should know what it is. It's y equals minus x line, right? Alternatively, you could find out the equation. The y-intercept is 0. Find the gradient and then use y equals mx plus c. Or since this is a very common line that you do reflection about a lot of times, you should remember that this is y equals minus x, right? It has a gradient of -1 and it's passing through origin. It's y equals minus x. Okay, now it says triangle A is mapped onto triangle C by rotation 90 degrees anti-clockwise about the origin. On the diagram, draw triangle C. Okay, now you will always be doing this with a pencil. Do not use a pen for this. So the working that you did in the first part, now let's reduce that clutter. Let's remove what is not required anymore. Let's remove these lines. We will erase them because we'll be doing these with a pencil. So we'll erase these. Okay. Line of reflection as well. They just wanted you to describe that. You've done that now. You can erase that as well. And now let's focus on the second part. That's what you have to draw on the diagram now. There is a rotation about the origin. So 90 degrees rotation about the origin, 90 degrees anti-clockwise rotation. Where is triangle C going to be? How do we think about this? Let's look at one point at a time. So point Z, it is 2 units right and 1 unit up, right? 2 right, 1 up. We have to go anti-clockwise. So one way to do this would be what we discussed that day, if you remember. This is up, this is down, this is left, this is right. And then Z is 2 right from the origin and 1 up. If you're going anti-clockwise, this is the direction that we're going to go in. Right goes up, so it becomes 2 up. And up goes left, so it becomes 1 left. So from the origin, you go 2 up and 1 left. And that is where the point Z prime is going to be. Okay. The alternative is to just rotate these lines like I'm doing here. So this is the origin. Rotate this yellow thing 90 degrees anti-clockwise. That's fairly straightforward to do, right? It'll become this. So that's the point Z prime. All right. Okay, let's move on. That was Z prime. Now, what about Y? Y is like this: 1, 2, 3, 4, 5. 5 units right and then 1 up. 5 right, 1 up. Now, when this red thing is rotated, what is that going to become? 5 up and 1 left. And that is your point Y prime. That's where it goes. Okay, so just rotate this thing 90 degrees anti-clockwise like this. And that gives you Y prime. Okay. Then you've got X. X is 1, 2, 3, 4, 4 right, and then 2 up. Rotate this red thing 90 degrees anti-clockwise, becomes 4 up and 2 left. And that gives you this point X, X prime. And that is going to give you that transformed triangle now. This is the rotated figure. Okay, you can label this now. This is triangle C. That is what we were looking for. All right, so it's rotated 90 degrees anti-clockwise about the origin. Make sense? Let's move on. Let's look at the next one. Okay, question number 11 from the other one. Let's try this. Describe fully the single transformation that maps triangle A onto triangle B. Okay, again, we have to see what transformation maps A onto B. What's the thinking process again? Is the size of the figure changing? No, it's not enlargement. Is it translation? It's clearly not a shift because the orientation is also changing, right? So it's not translation. It's one of reflection and rotation. How do we identify which one of the two it is? Join corresponding points. Let's say this is x, then this is the corresponding point x prime, or a onto b, so it will be the other way around. This is x and this is x prime. Then this the point that is closer to x, let's call that y. So this would be y prime then. And the last point, that's z prime. Let's join corresponding points and see what we get from that. X and x prime, y and y prime. Well, they are clearly not parallel. That means it's not a reflection. Since it's not a reflection, the only other possible choice that we're left with now is rotation. It is a rotation. Okay, it's a rotation. Now, how do you think about rotation? One possible idea is using perpendicular bisectors. So you have to find the center of rotation first of all, right? So we have identified that it's a rotation, right? Now, what rotation? We need center of rotation and the angle anti-clockwise or clockwise. How do you figure out the center of rotation? One longer way of doing this is drawing perpendicular bisectors. That will work. You can do that if you want. But let's try it without that first, okay? And see if you can figure it out without that or not. Sometimes you can figure it out without it as well. If the center of rotation has integer coordinates, and that's mostly the case, you can just guess that as well. Okay, let me show you how. First of all, for guessing, you will need to think about what angle the transformation is happening at. So YZ was vertical here. That's becoming horizontal. So let's just take this side. That will help us understand this. So YZ was like this earlier, right? It was vertical with Z here and Y here. And then after transformation, it's becoming this. It's becoming Y prime, Z prime. So this Z has to go there basically, right? So that it becomes horizontal, right? Z has to go there. So what angle it is going to be? So remember, it can't be the other way. You can't have Z going here because that will make Z on the left. That will put Z on the left side, Y on the left, Y on the right side. That's not what we need. Z has to be on the right side in the transformed figure. And that can only happen if you go like this, you take Z to this side. That is anti-clockwise, 90 degrees anti-clockwise rotation. Okay. 90 degrees anti-clockwise. All right. Now, if you have to rotate this anti-clockwise like this, that means that the center of rotation is going to be somewhere in this region, right? Somewhere in this region. So now you can try to guess a point in this region. Let's try some points. Let's try this point. This is Z, this is Z, no. So distance from corresponding points should be the same for the center, right? So this point is not working. Okay, let's try another point. This is not going to work. This does not work. This, okay. So for Z, it seems to work. Let's check. So Z is 1, 2 and 2, 1. So Z is the same distance on both sides from this point. Okay. Now this is a potential point that we can have. Let's check the other ones. Y 1, 2, 1 here, and then 1, 2, 3, 4, 5 here. Okay. Then here 1, 2, 3, 4, 5, and 1. Okay. So 1, 5, 5, 1. Y is also the same distance. All right. What about X now? 2 units, and then 1, 2, 3, 4, 4 units. 1, 2, 3, 4, 4 units, and 2 units. Okay. So X is also the same distance on both sides. That means this is your center of rotation. Okay, so that's one way to directly identify what the center of rotation is. Try some points and see which point has equal distances from corresponding points. So this is supposed to be the center of rotation. Okay, that's one idea of just, trying some points and then using trial and error, you just spot that center of rotation like this. Okay. The other idea is, of course, the more formal method in which you draw perpendicular bisectors. Perpendicular bisectors of corresponding points. So you would join y and y bar. Perpendicular bisector of that, you draw that perpendicular bisector. What is that going to look like? It's 5 units, 6 units right, and then 4 units up. Okay, so from this point, 6 down, and 4 this way. Okay, so this line is like this, 3 and 2. On the other side, it will be 2 and 3. So it will go like this. The perpendicular bisector is going to go like this. Okay, you can draw it using a compass. Since I can't do that here, I'm just trying to think about the x and y components of the vectors. This is what the perpendicular bisector of y and y prime is going to look like. So I've drawn that first, and then you then you draw the perpendicular bisector of x and x prime. Perpendicular bisector of x and x prime, that's the midpoint. It has to pass through here, and that is going to look like this. Perpendicular bisector of x and x prime, that will go like this. This is where they intersect. You can draw perpendicular bisector of z and z prime as well. This is the midpoint, and that's going to look like this. So draw perpendicular bisectors where they intersect. That's going to be the center of rotation. You can try this using a compass and draw that perpendicular bisectors. You would figure out that this is your center of rotation. Now, once you figure out the center of rotation, what about the angle? Join any two corresponding points. So if I join the center of rotation with any corresponding points, let's join this and this. Although we already figured this out before, but just to confirm, this is what it looks like, right? This was the original point. This is the transform point. So how do you go from that original point to the transform point? That's a 90 degrees rotation anti-clockwise. So how do you write that now here? You would say it's a 90 degrees anti-clockwise rotation. 90 degrees anti-clockwise rotation with center of rotation at this point 1, 1. That's the center of rotation. Okay, so that's how you would describe it. It's 90 degrees anti-clockwise rotation. You can write it more clearly with 1, 1 as the center of rotation. Okay, so that's how you identify this rotation and the center of rotation. Let's move on. It says triangle B is mapped onto triangle C by a translation vector. -2, -3, draw and label triangle C. That's pretty straightforward. B is mapped onto another triangle with a translation. 2 left, 3 down. Okay, let's take any point. Let's take Y, for instance. 2 units left, 3 units down. That's the corresponding point for Y. And then Z, 2 left, 3 down. That's going to come here. And you can draw X accordingly. 2 left, 3 down. This is what the triangle turns out to be. They've asked you to label this as C. That's the triangle C. Okay. Then it says triangle A is mapped onto D by reflection in the line Y equals X. Okay. A is mapped onto D by reflection in Y equals X line. Now, what is y equals x line? Y equals x line is going to look like this. It passes through the origin 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and so on. That's the y equals x line. You have to reflect triangle A in this line. Okay, how do we do that? X, so now we have to look at diagonal distances, right? X is 1 unit away diagonally. It goes to the other side, 1 unit away. This is going to be the corresponding point for X. Y is 2 units on that side. It goes 2 units on this side. That's the other point. Let's call this X double prime, this Y double prime. And then Z, it's half a unit here diagonally. On the left side, it goes half a unit on the other side. And that's going to be the corresponding point for Z, and the reflected triangle will look like this. This is the triangle D. Okay, now you can remove those extra lines. This is what it looks like. All right. That's the triangle D reflected. That's the triangle A reflected in y equals x, which becomes triangle D. Okay, let's move on. Now it says triangle E is geometrically similar to triangle A, and its longest side is 12 centimeters. Calculate the area of triangle E. Now, how can we do that? The longest side of that is 12. It's similar to A. What's the longest side of this A triangle? Longest side of triangle A, that is 3 units. This is 3 units. Okay. So what we can say is A1 over A2, that should equal L1 over L2 whole squared. Okay. We have to find the area of triangle E. Let's call this A1. All right. Now, there are two ways of thinking about this. You can either find the corresponding lengths, find the base and height of this triangle, find the area of this triangle, and then use that in the other one. Or you can find the height of the bigger triangle and then use the area formula. So let me explain what I mean by that. Let's first find the area of this given triangle. Can we find that this triangle A, what's the area of the triangle A? If we consider YZ as the base, height is going to be perpendicular to that. This would be the height. That's 1 unit. So this is base, 1 unit, this is height. The area of triangle is going to be half into base into height. So we can say area of the triangle A, that is half into base into height, and that gives us 3 over 2 or 1.5. That's the area of this triangle. So we can say A1 over 1.5, that should equal L1 over L2, corresponding sides. This triangle has, the bigger triangle has a length of 12. Our triangle here, the longest side here is 3 units. So we say it becomes 12 over 3 whole squared. And that should give us the result. The area of the bigger triangle, that's going to be 16 times 1.5, right? Because this is 4. 4 squared is 16. 16 times 1.5, that is 24. And that's the area that we were looking for, 24 centimeters square. That's the area. You can use similarity to find that area. That's one idea. Okay, that was this question. Let's move on to another one. Okay, let's try this. Okay, let's look at this now. This is the next one. The diagram shows triangle D. An enlargement with center 5, 4, scale factor 2 maps D onto E. Center at 5, 4, that is this point here. It maps this triangle onto triangle E. Scale factor is 2. This current point, it remains here. It's not going to change, right? The point that is on the center of enlargement or the center of rotation, that normally stays in its original position. So this point remains there. Scale factor is 2. Look at this distance. Whatever is this distance, you multiply this by 2. That's going to be 1 point of that bigger triangle. And then similarly, whatever is this distance, you multiply this by 2, you extend this line, and that is going to take you here. That's the other point of that bigger triangle. And the bigger triangle is going to look like this. This is your enlarged triangle with scale factor 2 and center of enlargement at the point 5 and 4. Okay, that's what it looks like. This was 4. So this point here is 5 and 4. This is what we get. Okay. Now it says enlargement with center 5, 4, scale factor 0.5, maps D onto F. Draw and label the triangle F now. Now D is mapped onto F. The scale factor is now 0.5. What is that going to be? Now we also have to label that, by the way. Let's say that this is E, the bigger triangle. Then the smaller scale factor is 0.5. Whatever was the distance from the center earlier, now it becomes half of that. So let's mark these points. Let's say this first point. Okay, let's say this was point X, and this was point Y, and this was Z. So in the first transformation, you got these points. In the second transformation, where is Y going to go? Its distance is going to be half from the center of rotation now. So that point is going to come here, right? It was 2 units diagonally earlier, now it becomes 1 unit diagonally. So that's Y prime. And then Z, you just halve that distance. Where is that point going to go? That will be right here. This is Z prime. And your second triangle, that looks like this. This is the triangle you get after an enlargement with scale factor 0.5. Let's label this F. That was the second thing that you were supposed to do. Now it says triangle G has vertices 5, 4, 4, 3, and 3, 5. So there's some triangle G. It has vertices 5, 4, 4, 3, and 3, 5. Okay, let's think about that. 5, 4 is the same point. 4, 3. 4 and 3, that's another point. And 3, 5. 3, 5, that's another point. This triangle is triangle G. Okay, now this is G. Okay. F can be mapped onto G. F can be mapped onto G using a single enlargement. F can be mapped onto G using a single enlargement. Triangle F can also be mapped onto triangle G using a different single transformation T. Okay. Describe fully that single transformation T. Okay, so how do we think about this? Now, this is an important one. It says F can be mapped onto G using a single enlargement. Now, what enlargement? The size is not changing. From F to G, the size is the same, right? It's not really changing here. How can we call this enlargement? Let's think about the points. If this point is X, this is Y, what's the corresponding point to Y? Y is the closer point to X, right? So that Y point is going to go here. And the Z point is going to go here. This is the corresponding Z point. So Y is going here and Z is going here, and X is staying in its current position. It is basically an enlargement with its center at the point X and scale factor -1. Why -1? Because the figure is going on the other side, going to the other side of the center, right? F is on one side of the center, G is on the other side of the center. So the scale factor is going to be negative. And since the size is not changing, the size is the same, right? That means the scale factor is 1, that we're just multiplying the sides with 1. That keeps the sides the same length. So the enlargement that they're talking about, this is basically with scale factor -1. This enlargement has a scale factor of -1 and the center is at x. Now, is there another transformation that can also map f to g? Can we think of another transformation? That other transformation would be, this is point y, this is going to this point. Z is going on the other side as well. Y going to this side, Z going to that side. What kind of transformation is that? It's a 180 degrees rotation. That about this point, Y is going to the other side, Z is going to the other side like this. It's a 180 degrees rotation. Okay? Because using that, this point can go here and this point can go here. What's the center of rotation? Point X would be the center of rotation because X is not changing, right? X is staying in its original position. So X is not moving. That's the center of rotation. Y is rotated 180 degrees. Z is rotated 180 degrees to get that transformed triangle. So what do we write then? What's the transformation T that they're talking about? It's a rotation. It's a 180 degrees rotation. In 180 degrees, it does not matter whether you do anti-clockwise or clockwise. They're both equivalent. It's a 180 degrees rotation with center of rotation, at the point X, which is 4 and 5. No, 5 and 4. With center of rotation at 5 and 4, that's the transformation that's happening there. Okay, and that is actually something that's true in general, which I would recommend that you actually remember. Enlargement with scale factor -1, enlargement with scale factor -1 is the same as 180 degrees rotation. These two are always equivalent, given that the center of enlargement and the center of rotation, they are both the same. Okay, so centers should be the same. Whatever is the center of enlargement, it should be the same as the center of rotation. When that condition is met, an enlargement with scale factor -1 is equivalent to a 180 degrees rotation. These two are same transformations. Okay, now that's an important result that you should keep in mind. Enlargement with scale factor -1 and 180 degrees rotation, they are both going to be the same thing. All right, let's look at the next one now. Okay, let's try this. We have these shapes A, B, and C drawn on the grid. Shape A is mapped onto B by a reflection. This write down the equation of the line of reflection. How do you write down the equation of the line of reflection? You can just spot it just by looking at it, right? Or you can use a formal method, join corresponding points, mark their midpoints, and join those midpoints. This is the line that we're talking about. This is the line of reflection. Right? Join corresponding points and mark their midpoints. And the line that passes through the midpoints, that's the line of reflection. What's the equation of this line? It's a horizontal line. If horizontal lines are of the form y equals some constant, what's that number? That's -1. The line of reflection is y equals -1 here. Describe fully the single transformation that maps A onto C. A onto C. Now, it's clear that it's supposed to be an enlargement, right? Because the size of the figure is changing, it's increasing. So it has to be an enlargement. How do you find the center of enlargement? You join corresponding points. Let's consider this corner. Let's join these corners. Let's see what we get from that. Okay. And take another set of points. For instance, you could take these 2 points. Right? These are also corresponding points, this point here and this point here. Where are they meeting each other? These 2 lines are meeting at this point here. That's the center of enlargement. You can join the other points as well, and they will all pass through this point. You can check that. Maybe draw another just to do verification. If you join these points, you see that's also passing through C. And if you were to do the last one as well, all of them pass through that same point. So that's the center of enlargement that we were looking for. So now we can say it's an enlargement. It's an enlargement with center of enlargement at this point. It has coordinates -3 and 2, right? Center of enlargement at -3, 2. And what about the scale factor? That's the other thing that you have to write down. What about the scale factor? Look at any corresponding side. This side, for instance, is 1 unit. This is 3 units. This is being mapped to that A to C. So the side is getting multiplied by 3. Okay, so the scale factor has to be plus or -3. Is it minus or plus? It's minus because the original figure is on one side of the center, the transformed one is on the other side, and the figure is also getting inverted, right? So the scale factor has to be negative. We say this is -3. That's the scale factor. Okay, so that's how we describe this transformation. The next part is matrix. That's not part of your syllabus anymore, so we will skip that. Let's have a look at just 1 or 2 more, and then we end. Let's look at a couple that involve combinations of transformations now. And that's it for today then. Let's have a look at this one. Describe fully the single transformation that maps A onto B. Transformation that maps A to B. Now, what transformation is this? I think it's fairly easy to recognize that it's a reflection. If not, you can just do that standard process. Is it a translation? No. Orientation is changing. It's not an enlargement. Size is not changing. What about rotation and reflection? You can join corresponding points and see if these lines are parallel or not. We are getting parallel lines. That means it is a reflection. What's the line of reflection going to be? Just find the midpoints of these lines. This is 1 point. This is another point. Join those midpoints, and that's the line of reflection. The line of reflection is this one here. It's y equals -1. So how do we describe this now? We say it's a reflection in y equals -1. That's the reflection that we're talking about. Okay. Now, part B is matrix, is related to matrices. We will skip that. Now it says transformation M is the reflection in the line x equals 2. Transformation M is a reflection in the line x equals 2. Transformation R is a rotation 180 degrees about the origin. We have 2 transformations given here. Okay. A, which is this triangle, is mapped onto D such that Rm of A is equal to D. Draw and label triangle D. Now, what does this notation mean? Rm transformation is applied on A and the result is D. Okay. In what order do we apply these transformations? M is closer to A, so M applies first. So this transformation has to be applied first, and then you apply R after that. This transformation has to be applied second. Okay, so you do these 2 transformations. on the triangle A. So first of all, reflect that in the line x equals 2. Let's start with that. Reflection in the line x equals 2. What's the line x equals 2? It's a vertical line. That's the line x equals 2, right? We have to reflect triangle A in this line first. What does that become? It's going to be a triangle like this. Right? This is what happens after that first transformation. You get this triangle. All right. And then you have to do a rotation of 180 degrees about the origin. Rotation 180 degrees. How does that work? You can do it directly. This point here is going to go. So remember, origin is the center of rotation, right? Origin is the center. It's 2. This point is 2 units on this side. It goes 2 units on the other side, and that goes to -2. And then this point here at 5, it's 5 units above the origin. It goes 5 units below the origin. That's this other point. And then finally, this point here, it's this distance on one side. It goes the same distance on the other side. That will be the other point on the other side. Let's mark that. So what does the transformed triangle look like? This is the final result that we get. This is triangle T. Okay. It's the final result that we get after applying those two transformations. Okay. Let's do one last now. One last one. This is this one. It says the perimeter of triangle A is A plus square root of B, where A and B are integers. Find the values of A and B. Okay, perimeter of this triangle. What's perimeter? Perimeter is just the sum of all sides. This side is 2, this side is 1. Hypotenuse, what's that going to be? Using Pythagoras, base square plus perpendicular square root of that, that's square root of 5. So this side is square root of 5. So what's the perimeter going to be? 2 plus 1 plus square root of 5, and that gives us 3 plus square root of 5. Compare that with A plus square root of B. What's the value of A that we get? A is 3, B is 5. Okay, that's the first part. That's simple trigonometry, just Pythagoras basically. Now it says triangle A is mapped onto B by the translation T. Okay, A is mapped to B. A is mapped to B. By a translation, write down the column vector that represents T. Take any corresponding, any two corresponding points. Let's take this point here and this point here, for instance. 1, 2, 3, 4, 5, 6. 6 units left. 1, 2, 3, 3 up. 6 left, 3 up. That means -6 and 3. That's what the vector is going to be. Okay, -6 and 3. In order to go from A to B. All right, let's move on. Now it says, describe fully the single transformation that maps B onto C. Single transformation that maps triangle B onto C. Okay, so we have to go from B to C now. How does that work? Is the size of the figure changing? No. Is it a translation? Doesn't look like it. The orientation is changing, right? So it's either rotation or reflection. How do you differentiate between the two? Let's join corresponding components, the corresponding vertices. 90 degrees vertex is this, and this is the 90 degrees vertex here. Let's join these 2 points and see what we get. We get a line like this. Okay. Then from the 90 degrees to the shorter side, we have this other point. Okay, so it does look like it's a reflection, right? Because the corresponding points, when we join them, we are getting parallel lines. You can confirm this with the third line as well, but it is, in fact, going to turn out to be parallel. as well. So these are parallel lines. That means it has to be a reflection. How do you find the line of reflection? Now, find the midpoints of these lines. Let's find the midpoints. 1, 2, 3, 4, 1, 2, 3. Okay, so this is going to be the midpoint of one line. And then for the other line, it's going from -5 to 4. This is the midpoint of the other line. You join them and you get that line of reflection. That line of reflection is going to look like this. This is the line of reflection that you get. What's this line? You should be able to recognize this just by looking at this. This is y equals x line, right? Gradient 1 passing through the origin. It's y equals x line. So how do you describe this transformation then? We say it's a reflection in the line y equals x. Okay, so B to C, that's a reflection in the line y equals x. Let's move on. Now it says, describe fully the single transformation that maps B onto D. So now we have to go from B to D. How can we do that? B to D. Now that's clearly an enlargement, right? The size is changing. B to D. Join corresponding vertices to find the center of enlargement, right? That's how we used to find the center of enlargement. Join corresponding vertices, the 90 degrees vertex to the 90 degrees vertex. That's this. Then the shorter, the vertex on the shorter side, that's this. Let's join these two. Like this. Where do they intersect? They intersect at this particular point. This is the center of enlargement. You can check this used by joining the third point as well, and that also passes through the same point. So the point of intersection, when we join these corresponding vertices, turns out to be this. So that's the center of enlargement. Okay, so now we know the center of enlargement. We know that it's an enlargement, and we know the center of enlargement as well. What do we do now? Okay, this is the center of enlargement. Now, let's write that down. We say it's an enlargement with this point is it is -4 and 2. -4, 2 as the center of enlargement. As the center of enlargement. And scale factor. What about scale factor? Look at the original figure. Smallest side here, this is 1 unit. The other figure, 2 units. So it's becoming twice. Scale factor has to be either plus or -2. But since the transformed figure is going on the other side of the center of rotation, the scale factor is supposed to be negative. So we say the scale factor therefore is -2. That's the scale factor. Okay. Then the next part is about matrices. I'll skip that. Now, this is an important one. That's what we're going to end with, the last part. It says the transformation V is a reflection in the line y equal to 0. Okay, so that's transformation V. It's a reflection in the line y equals 0. And then transformation W is a rotation 90 degrees clockwise about the origin. 90 degrees clockwise about the origin. The single transformation X is equivalent to the transformation V followed by the transformation W. Now, how do you understand that statement? Transformation V followed by transformation W. So what's happening first? V has to happen first. V has to be applied first, and W has to be applied second. If you were to write down in that notation, you would say this is WV transformation on something, right? So WV means V applies first and then W applies. Okay, that's what is happening. So it's X is a combination of V and W. The point GH is mapped onto P by the transformation X. G is mapped onto X. Find the coordinates of P. Now, how do we do that? The point has coordinates G and H. Now, where do we mark G and H? If we had a specific point given, then that would have been much easier, right? But they've not given us the point. They've just mentioned two letters like this, that one coordinate is G and the other is H. Now, let's investigate this. We have the diagram given. Let's investigate using this diagram. So let's mark the point GH anywhere. Okay, so let's take any random point on this diagram. Let's take this point, for instance, or let's take something positive that will be easier to understand. Let's take a point here, let's say. Oh, so this point is 1 and 3. Okay, now I'm going to write on the side GH. We want to write down the result in terms of G and H. We are taking a specific point, 1x coordinate and 3y coordinate, just to understand what it's going to look like. Okay, and then we'll convert that to something in terms of G and H. This is the point. Now, if you reflect this point, no, what's the first transformation? Sorry, the first transformation is a reflection in the line y equals 0. What's y equals 0 line? Y equal to 0, that's the x-axis, right? Y equals 0 is a horizontal line. It's going to be the x-axis, right? This is the y equals 0 line. Reflect this point in x-axis. Where is this going to go? This goes right here. This goes to 1 and minus 3. Okay. So 1 and minus 3, what does that mean? G remains the same and H becomes minus H. That's after the first transformation, V is applied. Okay. Now, once you have this point, what's the next thing that we've got to do? The other transformation is rotation 90 degrees clockwise about origin. 90 degrees clockwise rotation about origin. 90 degrees clockwise, okay, about the origin. This is the origin. We have to do 90 degrees clockwise rotation. How do we do that? This point is 1 unit right and then 3 units down. If we do clockwise rotation, how does this become? This is going to be 1 down and 3 left. Okay, so it is going to become 1 down and 3 left like this. When we rotate this 90 degrees clockwise. Okay, so this comes here and this goes there. That's what we get. So the point now becomes this one here, which is minus 3 and minus 1. So that point goes right there. So now this becomes minus 3 and minus 1. So what's happening to this now? It was 1 and minus 3, and now it becomes minus 3 and minus 1. So the y coordinate is now becoming the x coordinate. All right. So we can say minus h. Now that becomes this. And what about 1? That is going and becoming the y coordinate. So that's becoming g, but its sign is also changing. That's minus g. Okay, so you can do it directly like this. You can think of that directly like this as well. It was 1, 3. Then it becomes minus 3, minus 1. So you're switching the points. You're switching the coordinates, and also you are changing the sign. Okay, so it becomes minus h and minus g. That's what they asked us in this part. First of all, the coordinates of p, that is going to be minus 8 and minus g. That's the transformed point, minus 8 h and minus g. Now, what's the single transformation? What's the single transformation that will map this point to this point? That's the question. Single transformation that will map this point to this point. How can we think about this now? 1, 2, 3, 4. what's the single transformation that maps that point to this point? Okay. Actually, there are multiple transformations that could get you to this point. So you can't be sure. For example, one transformation could be that you reflect in the line y equals minus x. Okay, 1, 2, and then 2 units on the other side. So that could be one transformation. Another less obvious one could be that you rotating about this point 180 degrees. But generally, when they ask these questions, something is happening on the standard reflections or rotations. For example, if it's a rotation, it's about origin. If it's a reflection, it's in one of the standard lines. But to make it uh, easier and to make sure that you are getting the answer correct, a good idea would be to take another point as well, okay, and see what happens to that other point. So for instance, let's apply the same operations on another point, and that will make it clear which specific transformation it is going to be. I'm going to take another point. Let's say I take this point here. Okay, I have another point here. Reflected in the x-axis, first of all, that gives me this point here. Then rotate it 90 degrees clockwise. So it's 2 right, 2 down. It's going to become 2 down, 2 left. That one is going to go here. What that means is, if you had a line like this, after that transformation, it becomes this. So now that makes it clear it cannot be a rotation, because if this was x, then this is x prime. And if this was y, then this is y prime. Y is coming here, x is coming here. It has to be a reflection. It's a reflection in the line y equals x. If you reflect it in this line, x becomes x dash, y becomes y dash. That's the transformation that you have, and that's what you write down here. You say it's a reflection in this line. What's this line? This line is y equals minus x, right? So it's a reflection in y equals minus x, and that's your final answer. That's what you write here. Okay, now this was quite tricky, and it actually became trickier because they've taken out matrices from your syllabus. Actually, if you were to do the part E of this question, then part F could actually be done using part E, and that would have been done much quicker. Okay, so using matrices, this part would have become much simpler. That's why it's only 1 mark and 2 marks, although it required a lot of effort from our side. Now, if it comes without the matrix part, so if they had not asked us for this part E earlier, and we had to do it directly, then this would carry more marks because it requires more thinking in this case. Now, without matrix, it becomes quite tricky. Okay, so that's why it took us that much time, because in the original paper, they would have expected students to be able to do it using the matrix in the previous part. But since matrices are not part of our syllabus anymore, we wanted to do it directly, and that's how it would work using inspection. So this is 3 marks right now. It should have been at least 5 marks if there were no if the part E was not there. Okay, so that's why you would have to think of all of this. So that's it for today. We've done enough practice. I think we will end with this here. And in the next session, then we will most likely be starting graphical solutions, or one of the other topics that we are left with. And then we are starting yearly past papers right after Eid, inshallah. If we still have any topics to do after Eid, what we will do is we will start with the past papers anyway, right after Eid. And the topics that we are left with, we will continue doing them for another week alongside, in parallel to that. Okay, but I would want to start the yearly past papers by the first week of April. So essentially right after Eid, just a couple of days after Eid, inshallah. All right, so that's it for today. I'll see you again in the next class. If you have any quick questions, you can let me know. Otherwise, we end this here. Any problems? No? All right, good. So that's it for today then. I'll see you again on Monday. Allah Hafiz.